Hi, welcome back. Let's dive into a very relevant concept in electricity, the electrical potential. We already introduced the idea of the electric field. This is a perturbation in space created by all electrical charges. This electric field is felt by other electrical charges. As a consequence, these other charges experience Coulomb's force. The electric field is a vector field, which means that we can visualize space as filled with vectors, tiny arrows covering the whole of space, pointing in the direction from positive charges to the negative charges. Electric fields start at positive charges and end in negative charges. The direction of the vectors can be joined. This is known as the electric field lines. These field lines indicate the direction of the vector field. At each point, electric field lines go from a positive source to a negative sink. Electric field lines indicate the direction of the force that a positive charge would feel. Now that we have this visual interpretation of the electric field, let me introduce the electric potential. But first, let me diverge a little to introduce this idea. Imagine that you are playing golf and you put a ball on the green. If the spot you put the ball is flat and horizontal, it will stay put. The ball will not move. The ball will experience no force. If you place the ball at a spot that has a slope, the ball will roll down the slope. The ball will feel a force that will make it move. The steeper the slope, the greater the force, and the larger the acceleration of the ball. We can draw the heights of the green on a map, and we can join all the neighboring points that have the same height, like this. This way we have lines that correspond to the same height. If the ball is placed, for example, at this spot here that is a minimum, surrounded by higher heights, the ball will not move. If we place the ball in this other spot that is a maximum of a hill, because right at the maximum of the hill the slope is horizontal, the ball feels no force, the ball does not move. If we put the ball in this other spot between these two lines of height, the ball is at the slope and the ball will move towards the lowest height. The ball experiences a force that makes it accelerate and move. We can say that the gravitational force or the gravitational field exerts a force on the ball that makes it accelerate. Let's now talk about electricity. The electric field is a vector field that at each point in space has a magnitude and a direction. We have a space filled with arrows that represent the electric field. The magnitude of the arrow represents the magnitude of the electric field and the direction of the field. The vector field and the force are proportional. Let's check these equations. Force is conservative. This means that it does not dissipate energy. There will be transformation of energy, but the overall energy will be conserved. When you were studying potential energy, you were introduced with the powerful relationship between the conservative force and the potential energy. The force is the negative derivative of the potential energy with respect to the position. In 3 dimensions, we write it using the Greek letter nabla, which represents the 3-dimensional derivative with respect to position. We call it the gradient. So in 3 dimensions, we said that the vector force is the negative gradient of the potential energy. For example, for the gravitational force, we had that the gravitational potential energy is given by minus g times m prime over r, where the gravitational force is g times m prime over r squared. Check that one is the derivative of the other one with the opposite sign. Back to the electric field. Because the electric force is a conservative force, we can derive this force from a potential energy and vice versa. So if we integrate the force between two positions, let's say infinity and r, we find the electrostatic potential energy. Which reminds us that of the gravitational potential energy. But here we can have positive and negative potential energy depending on the charges involved. Now let me introduce a final concept. Just as we introduce the electric field as the electric force per unit charge, this electric field is independent of any test charge, or independently of if there is a charge there to fill anything. I introduce the potential V as the potential energy per unit charge. This will be independent of the presence of any test charge. With this in mind, we can write now back to the beginning of this lesson. You can visualize the electric potential as that map of heights, which in this case is a map of potentials, where if there is a charge in that map, the charge will feel the gradient of the surfaces of the map. The gradient of the potential is the electric field. So the electric field points in the direction of greater slope in that potential map. Putting all of these together, we have that E is equal to minus nabla of V. The electric field is minus the slope of the electric potential. May science be with you.